I think it's time to start. Thank you for coming and for inviting me. Give this mini course of the lectures about the elements of Nijenhuis geometry and applications. Uh, it's a part of the modern differential geometry, or how it's called, like also the geometric analysis or tensorial calculus and the other important names, let's say. Uh, I'm planning to give us three lectures. The first lecture will be about some basic things, definitions, and theorems in Nijenhuis geometry, with the motivations, with some I don't know ways for the applications. Second lecture will be about the integrable Hamiltonian systems. I will prove Liouville's theorem about the Liouville integrable systems. And in third lecture, we'll study the geodesic flows and how they are related with Nijenhuis operators, Nijenhuis geometry, and the other important applications also, how to construct the integrable systems. And I will give some reference about the infinite dimensional integrable systems that, for example, KDV, Kamasa-Holm, but we will not touch this area. So let me start from some motivations and some uh, definitions, I don't know, of the subject. So from Felix Klein, we know that the modern differential geometry, it's so the first part is motivation. From the Felix Klein, we know that the modern differential geometry, it's some manifold. Manifold and some structure. Structure, it's usually some tensorial structure. Uh, And the geometry is called by names of the structures, am I right? So, for example, if you have a symmetric non-generate bilinear form, bilinear like tensorial field like this, it's called Riemannian or pseudo-Riemannian geometry, depending from the indexes of this bilinear form. If you have the skew-symmetric bilinear form, non-generate and closed, it's a symplectic structure, it's a symplectic geometry. And if it's we have the skew-symmetric bilinear form on cotangent bundle, and with some extra conditions, it's a Poisson geometry. And the geometry is called by the names of the structures. Yeah? If you have them additional structures, it's a Kähler manifolds, Riemannian manifolds, symplectic manifolds, um, complex manifolds, complex structures, and other very beautiful subjects, directions in a differential geometry. So differential geometry studies the manifolds plus structures. And up to the change in the structures, we can already find some very important connections between these other structures. For example, if you know that if you have metric, symplectic structure, and almost complex structure, and we know that there's a compatibility condition and other beautiful things. It's some motivation and what kind of mathematical apparat we have to study the kind of problems. It's in differential geometry, everything studies up to the coordinate transformations. So let us have local coordinates x1, xn. Then we can change the coordinates locally or globally, but almost everything we'll study it will be the locally. It's a local differential geometry. We can change to coordinates, and we'll have the Jacobian matrix of this coordinate transformation. Yeah, we studied everything up to this form. So let me give you some examples. If you have please questions, so please stop and ask every time in every moment you have. Don't wait for end of this lecture. So the first example that you already know, it's let G, it's a metric. So it's symmetric, yeah, non-generate, linear form, or tensor type of 0, 2. Then we are asking the important question. So we have some object on a contingent bundle, and we're asking the question when there exist the new coordinates u1, un, such that in these local coordinates u1, un, our metric has a very simple form. Like very simple form is a constant form, yeah? ij, it's a constant, some constant form. The answer is known from the Bernhard Riemann, his very famous talk that if and only if the curvature is zero, yeah? Curvature tensor is zero. Curvature tensor, let me remind you, it's a tensor uh, defining invariantly like this. And metric, yeah, it's flat. It's called a flat that if we can reduce to the constant form, if and only if the curvature tensor, the remaining tensor is zero, vanishing. Next, a very good example, and if we have now skew symmetric form, skew symmetric form, ij equals to minus ji, and non-generate, pardon, it's not zero. Yes, Q-symmetric bilinear form, non-generate. When this form is, let's say, flat, yeah, when we can brought this form to constant form. It's a Darboux theorem, which says that if and only if then this form is closed, yeah, and closed non-generate skew-symmetric form is called the symplectic form, so symplectic structure. So it means that symplectic structure every time is a can be brought to the constant form. And this condition when we asking question about for some tensor uh, can can we brought this tensor field to the constant form? It's we have the special term. It's called uh, integrable tensors. So when tensor of some type integrable, yeah. What kind of necessary and sufficient conditions we have to ask to answer this question? And the last example, it's a skew-symmetric bilinear form, yeah, Poisson structure on a cotangent space with up to indexes on cotangent bundle. When this schizometric bilinear form is flat, the answer is when the rank of this matrix, yeah, it's a matrix, n by n, rank of this matrix locally constant, and Jacobian identity holds. So rank locally it's a constant. So we are studying it in some neighborhood of some point, yeah, point P. Probably let's call this Q because P is a Poisson structure. And we're studying the locally, and if in this neighborhood of this point, the rank of this matrix is a constant, and Jacobian identity holds, then we can brought this Poisson structure to this structure. This structure is called Poisson structure to the constant form. And you can manage that we are studying the tensorial fields of the rank 2. Yeah, it's a tensorial fields rank 2. It's like metric, it's a tensor type of 0, 2. Symplectic structure is also Poisson structure is a tensor type of 2, 0. And the question is how about the tensors type of 1, 1? What about tensors type of what is the answer for tensorial field of type of 1, 1? Uh, tensor tensors type of 1, 1, let me remind you, it's operator fields. Yeah, it's not bilinear forms, it's operators. And uh, the answer is an X that let us have the operator field. And it's a tensor type of 1, 1. And we can brought to the constant form if and only if so there exist local coordinates u1, un, gz, lij. It's a constant. If and only if there is a three conditions. First of all, is like for any two vectors, we have this identity. It's a very strange identity, but we will see that it's not so strange. These conditions should be vanish. Second one is the eigenvalues are constant. And the third one is a kernel uh, distribution is regular and integrable. And integrable. So it's not easy answer like we had before for other examples, but to be honest, we have to understand that the operator fields they are more hard than bilinear forms. The reason is that it's a reason is from linear algebra. Yeah, it's why I'm propaganding for my students that study the linear algebra in a very good way, because that it's a very important subject, and from this very important subject we know that the operator fields, operators, they are more not easy objects because operators has a lot of invariants. Yeah, it's trace, determinant, and other coefficients of characteristic polynomial. It's eigenvalues and the other specific forms. So let's discuss the three conditions. So second condition we need because the eigenvalues are invariants and in every local coordinate system it's impossible to change them. Yeah, if they're not a constant, it's impossible to bring them to constant form because it's invariance of operator field. The integrability of the kernel and the regularity of the kernel distribution, it's also some kind of technique condition that we need because It's like from Jordan's theorem about normal forms of the operators. Yeah, we when we choose the basis, we look at this kernel distribution and choose there the bases. It's also some kind of technique condition, and there is one specific one. The first condition is very specific, and this is a necessary condition for operators. It's necessary condition that we can brought the operator to constant form. And from now we study Nijenhuis geometry and Nijenhuis operators. It was like some kind of motivation for it. Definition, the first and the basic one. So probably I should ask it before, but everyone knows what is a tensor and what I'm talking about. Or probably I need to remind the definition of tensors and how work with them.
So maybe here people are confident, but for the sake of people who will listen to the recording, maybe just a little brief summary will be good.
Okay, let me remind. Please don't be shy to ask questions if we are here to study something. Uh, what is a tensor? We have manifold and we have tangent space. Yeah, it's pairs of point x on manifold and the vector v x on a manifold. V it's some vector on a tangent space, and also we have a cotangent bundle xi such that x again on manifold and xi it's element of the cotangent bundle cotangent space on the point x. Then we can define the multilinear mapping. It's called MT from Cartesian product of the cotangent spaces, cotangent bundles. It's P and Q numbers of tangent bundle to the R. And from linear algebra, we know that what is the bilinear? Its mapping is linear from all arguments. And from linear algebra, we know that the bilinear form, yeah, it's a product of it's a mapping from the Cartesian product of the tangent space to R, and this tensor type of 0, 2. Yeah, and we can again ask here the questions about the symmetric bilinear forms, skew-symmetric bilinear forms, and study the bilinear forms on a cotangent bundle. But we had already example about it uh, with the Poisson structure. It's a tensor type of 2, 0. Yeah, and probably the most like important example here it's tensor type of 1, 1. The mapping from tangent bundle times to tangent bundle to R. It's a tensor type of 1, 1, and it's operator field. Probably the easiest way to explain why it's separator, it's if we look how tensor type of 1, 1 changes under the basis change, yeah, in linear algebra, then tensor type of 1, 1 changes like absolutely in the same way like operators, like in a new coordinates or new basis. It's like transition matrix minus one, operator in old basis, and the transition matrix. So it's a short remind what is a tensor. So here we study the operator fields, tensor type of 1, 1, such that an operator field L, yeah, tensor type of 1, 1, 1 up index, 1 low index, is called Nijenhuis operator. Nijenhuis operator. If for any two vector fields psi eta, Nijenhuis torsion, it's some definition, L square psi eta plus L psi L eta minus L psi eta minus L psi L eta vanishing, and this is called Nijenhuis torsion. Torsion. So, and uh, how I said before, we studied the manifold structure, and our structure is a Nijenhuis operators. So, operator fields with a vanishing Nijenhuis torsion. Probably you've seen these operators and this Nijenhuis torsion in uh, very different subjects, directions in math, for example, in complex geometry, when you study the complex structure manifolds, so there is a very famous theorem of Nylander-Nirenberg that claims that almost complex structure is a complex structure if and only if the Nijenhuis torsion is zero. Yeah, Nijenhuis torsion is vanishing. So, and but there is other very areas where you can really find it. And tomorrow and in the third lecture, in the next lecture and in the third, we will study the applications of this geometry because every new theory, in my mind, in my humble opinion, should solve some classic problems, and we will see that what kind of problems we can solve with studying the separator fields. The first man who introduced this Nijenhuis operators was Albert Nijenhuis. He's Dutch American mathematician. He studied questions about the integrability of the tensor fields, and there is a theorem of Hantis, Thompson's, Houghton, who works with him, who had theorems about the operator fields that diagonalizable in some coordinates and other very important stuff. But it's it's hard for it to fall. The first fact that this thing that I wrote here, it's really tensor. It's a tensor type of 1, 2, 1, 2. It's a good exercise to check that it's really tensor, but believe me, it is. So, and there is some several ways how we can rewrite this Nijenhuis tensor, Nijenhuis torsion. For example, if we have on manifold symmetric connection, yeah, symmetric connection, for example, Levich-Vita connection for some metric, then we can rewrite Nijenhuis torsion in the next way. let me remind you that the commutator of the vector fields in this case will be like this. So then Nijenhuis torsion, it's L nabla psi L minus nabla L psi L psi. Um, or we already read it in the terms of the covariant derivative, but there is exist another type of derivatives, for example, lead derivative, yeah, along the some vector field. So it's also Nijenhuis tensor can be understood like some mapping from the vector field to operator field, and in this case, the Nijenhuis torsion or operator L is Nijenhuis. If for any vector field psi, we have the L lead derivative of psi from L minus lead derivative from the L psi to L is a 0. Or in the local coordinates, I can lead derivative. In the local coordinates, we have I, J, K, yeah, 3 indexes. It's a very long formula, but alpha J, T, I, K, D, X alpha minus L alpha K, D, L, I, J, D, X alpha minus I alpha D L alpha K D X J my plus L I alpha J D X K. They are like equivalent. It's easy to check that just replacing the formulas to formulas. And today I'm always said like we'll study some basic theorems and some kind of like basic questions in every geometry or in every science we ask in math. But we'll start from the examples. Yeah, we need examples. Examples. For example, the constant operator field. Yeah, where Lij is some numbers. It's a Nijenhuis operator. Nijenhuis operator. I think it's an easy way to see it. It's from equivalent definition in local coordinates because we take a derivative of everything and the derivative of the constant it's 0 and every element of this part is 0 and it means that the Nijenhuis torsion is vanishing. The second good and important example it's a scalar operator. It's operator that we can take some function fx and multiply it for identity operator or fx. It's also Nijenhuis operator. It's also easy to check. Probably the best way is just put it this formula for the basic definition, the first definition that I give, and see that everything is a cancel. So the third example, it's a complex structure. So all complex structure J, yeah, J, complex structure. It's also Nijenhuis operator. And the last simple example, diagonal operators, like if in some local coordinates our operator is like this, then it's also Nijenhuis. Nijenhuis operator. Great. Uh, now I wanna prove and show some proposition that we will use for showing the normal forms for some type of Nijenhuis operators. And this proposition is the next. Next. So let's call it lemma. Lemma. Let L be a Nijenhuis operator. Then we have Lxi dt minus t dxi t xi t d trace L, where xi it's a characteristic polynomial of this operator, that t identity minus L, it's a t power of n minus sigma 1 t n minus 1 plus etc. etc. Minus sigma n. So it's a very useful formula for Nijenhuis operators to prove some normal forms, to find some good characteristic of this operator field. And we will prove this lemma now. So the first step uh, for any operator field not necessary Nijenhuis operators. We have the formula that for any vector field, the lead derivative of the determinant of operator L, it's can be found like a trace of comatrix of L multiplying for the lead derivative of L, where the comatrix it's a matrix such that the L to L it's yeah, it's a matrix of the uh, there is a Laplace formula how to find the inverse matrix. Yeah, inverse matrix. So and this is some kind of the half inverse matrix. So if you multiply it for your matrix L, then you take the not one, yeah, not identity. You will take the determinant. So if you divide this comatrix at matrix, it's like if you divide it for determinant of operator, you will take the inverse matrix. So it's this formula is also easy to prove. For example, one way it's like this determinant of L, yeah, can be found like this. Ij L Ij. Yeah, sum. It's how I said. It's just you take the minors and multiply it for this. And after it, if you like formally take a derivative, partial derivative by like this, then it will be element of our comatrix. Then if we take the full derivative along to the some parameter t, dt, and if we replace this from the above, then we will get that the psi j L I T I J dt. So it's a trace, yeah. It's trace, and we took this parameter t, but we can also take derivative along any vector field like eta. And then this formula is true. So first step is done. So we proved now this formula. Next step is to use this formula. Uh, let's eta will be L psi, then lead derivative eta determinant of L. Let me rewrite this formula once more. If you repeat this thing and use that our operator is a Nijenhuis, the condition that our operator is a Nijenhuis, it's that L lead derivative psi L equals to lead derivative L xi L. Then we have lead derivative L psi determinant L equals to race. Here, this L psi I will change for this side. Then this is a determinant, yeah, because comatrix to matrix, it's a determinant. Determinant L trace from L psi L, and then there is a property of the lead derivative that we can, it's this operation is a commute with taking the trace, then determinant L, lead derivative, trace L. So second step that we proved this formula. Second step that we proved that the lead derivative L psi that L equals that L lead derivative trace L. It was second step. Now, from the third step is that we should understand that this formula is equivalent for the next, that L dual operator from the differential of the determinant of L. It's a determinant of L multiplying to the differential of the trace. So probably I should ask the question like, everything is clear, or do I stop somewhere maybe and explain more? Okay, so why these two formulas are equivalent? It's from the next obvious property of lead derivative, some kind of definition of lead derivative. For any smooth function, yeah, and for any vector field xi, uh, lead derivative L xi from the function f. What is it? It's some vector field, new vector field, and we should derivative our function along to this vector field. So it's just L xi f. Yeah, or in another way, it's just uh, can be rewritten like this. Yeah, can be rewritten like this. And the f L xi, it's just acting the dual operator for this one form. So if we repeat now f, if we take like f like determinant of L, then our formula is true. Yeah, our formula is true. So, and the final step is that from this formula, from this formula, I wanna get the formula that I claimed in the here. I wanna get this formula. To do it, I need to just replace the final step. I need to just replace here L to T identity minus L. Then we have like T determinant of T identity minus L minus L star. So probably I need to change the signature. Yeah, like this. Here is a plus, here is a minus. Then here will be plus, here will be minus. From the, this is a characteristic polynomial, yeah. And the right side is a characteristic polynomial to the determinant, to the differential of the trace. So finally, L star to d xi t minus t d that it's a characteristic polynomial. Characteristic polynomial to d trace L. So that formula that I claimed and we proved. The main thing that we used that is operator is Nijenhuis is here. Here to prove this formula. Here we use it that L is Nijenhuis. So great. Now I want to discuss in my last 13 minutes about the singular and the regular points and prove one of the main theorems in this science that called the normal form of the differential non-generate Nijenhuis operators. So singular points. Singular points. Uh, we are studying the some tensorial field, yeah. It's there we have some smoothness conditions, and also we have some algebraic properties from the linear algebra because it's operator field, and it's a big reason why we separate this like singular points for two types: algebraic singular points and differential singular points. Algebraic and differential. Uh, Today we will not discuss about algebraic singular points. I think we will talk about it in a third lecture, and let's just keep it like this. So I will explain what is algebraic singular point next lectures. Today we are interested in differential singular points. What is differential singular points? Uh, Again, we have operator field, yeah. We have operator field and every operator field uh, has n naturally defined functions. Yeah, we already seen these functions. It's uh, coefficients of the characteristic polynomial. Yeah, it's Tn minus sigma 1 Tn minus 1 minus sigma 2 Tn minus 2, etc. minus sigma n. So this is a naturally defined function for any operator field, and it's invariants. They don't change under the coordinate transformation. Yeah, and these functions, this set of functions, define define some mapping from our manifold to Rn. So I can define mapping like this. Mapping phi from our manifold to Rn like this. We take the point on our manifold and calculate this point on a set of functions sigma 1 from P, etc., sigma n from P. Yeah, and we have a mapping from our manifold to Rn. And from the calculus, we know that every mapping has a Jacobian matrix. Yeah, it's a matrix d sigma I d xj. And what is a differentially non-generate point? Now we can define what is a singular and regular point in differential meaning. Definition, uh, point P on our manifold is differentially non-degenerate if the rank of df at point P is maximum, it's n. So it's a point where the invariants are stable. Yeah, the differentials of the invariants are stable, or the gradients are linearly independent. So there is a million equivalent ways to say it, but the meaning is clear. And it's a point differential non-generate, and mm, the point calls it differentially degenerate if rank drops at this point. Yeah. So if we write the opposite thing for this definition, it will get a singular point in meaning of differential conditions. They were my small steps in this science. It's started from the studying these kind of singularities, and there was a term. It's called the almost differential and non-generate Nijenhuis operators. It's operators. It's a the point P is called almost differential non-generate if the rank of this mapping drops for a one. So it means like the rank is n minus one. And in my bachelor and master theses, I did some steps in this way, and there exists some kind of good problem for this. So we are very open if someone wants to try or to try to solve or try to do something in this case. So it's a very fundamental problem, studying the singular points in differential meaning. So the theorem, the last theorem for today. Assume that L is differentially non-degenerate Nijenhuis operator at some point at point P, yeah, in some neighborhood of point. Then there exist the local coordinates x1, etc., xn, such that L takes following form. Following form. x1, 1, 0, 0, x2, 0, 1, 0, xn, 0, here the 1. So, and this form is called non-generate Nijenhuis operator form and its normal form. And to prove this theorem, it's like 5 minutes after this very useful lemma. First of all, we need to prove that for any Nijenhuis operator, for any Nijenhuis operator, we have this following relation that the JL equals to SG, where J it's uh, Jacobi matrix of this mapping, yeah, mapping of the invariants. S it's a matrix like this. Very similar for our L, but here we have the invariants, not the coordinates. Here is a, pardon, 0, here is a 1. So, if we can prove these matrix relations, and our theorem is very obvious because we assume that we are in some neighborhood differential non-generate point, it means that invariants are independent functions and we can take them like local coordinates. And if we take these invariants like local coordinates, then in these matrix relations, I can write like L G minus 1, yeah, because the J is invertible, because the rank is maximum, full. S J, then we will take this form because it's a standard uh, way how we can, like, yeah, it's not standard, it's like the rule how we change the basis of coordinates and for operator fields. To prove this relation, it's already, we already proved this relation, but we proved in this another way. We proved it like this. We have equivalent. We have equivalent formula, and it's just a matrix relation. So let me in the last 3 minutes explain why this matrix and this strange form are equivalent. Uh, Psi it's characteristic polynomial. Then d psi it's minus tn minus 1 d sigma 1, etc., minus d sigma n. Yeah, and if we reput it here and collect the powers of t, then we have the relations like this. For Tn, we have just identity, the sigma 1 equals to the sigma 1. For Tn minus 1, it will be L star d sigma 1 equals to sigma 1 the sigma 1 plus the sigma 2. And for any k, it will be like this. For power tk, we will have L sigma the L star the sigma k equals to sigma k the sigma 1 plus the sigma k plus 1. So, and if we really look at this matrix relation and write it and like multiplication, yeah, just like columns to rows, then we'll get this formula. So it's just one of the way how we can write this identity in matrix form. So I think we proved. If you have any questions, I'm happy to answer for them. The next lecture will be about the integrable Hamiltonian systems, and there we will prove the classical Liouville theorem, because in the third lecture we will use it. So yeah, thank you. I'll stop here for today.
Thank you very much.
Questions?
Could you repeat, please, what's the next lecture topic?
Next lecture, we'll study next week, lecture 2. It will be the integrable Hamiltonian systems. And the Liouville theorem. Liouville theorem. I hope that I read it correctly. Liouville theorem. And some examples, probably, if we'll have time for it.
Okay, thank you.
So, other questions? If there is no question, let me stop.